So how do we quantify the error in our linear regression or least squares regression? Well, in order to do that, I first just want to start off with two important points. And the first is that any line that is computed in the manner that we, well, other than the line that we computed from our previous example, we will have a larger sum of residual squares. That's the first point. The second point, I just want to talk about briefly what we've done so far. Okay, so initially we may have a set of data points that look something like this, where y and x, and we have a whole bunch of points that lie in our plot. Well, firstly, we can calculate the mean of this value, of this data set, that is y bar, and the difference between each one of these points and the mean tells us a measurement of the difference between the data of a single estimate and a single estimate of the central tendency of the data, or the mean. Then we carried out our linear regression, and here we ended up with a linear line that cuts through our data. And we calculated the sum of residuals, and that difference between the data points and this new line, that vertical distance, gave us another measure of the central tendency of the data. And so if the spread of the points around the line is similar in magnitude along the entire range, and the distribution about the line is normal, that is, it obeys a normal distribution, then the linear regression provides the best estimate of A0 and A1, and we call this the maximum likelihood principle. And then the measure of the standard deviation, or in this instance we actually call it the standard error of the estimate, becomes S yx equals square root SR divided by n minus 2. Now, the reason why I use n minus 2 is because we've lost 2 degrees of freedom when calculating A0 and A1. Okay, but now, what about the error of our least squares regression? Okay, now we've just spoken about the standard deviation or the standard error of our estimate, but we haven't actually mentioned what the error, or how we could quantify this error of the least squares approximation in a useful manner. And we're going to do that with something called the coefficient of determination. That is a value that we label r squared. Okay, so from the previous plots that I showed you, we had a mean y bar, and if we calculated the difference between the individual data points in this mean, that is y minus y bar, and we squared this, we could get an estimate for the total error squared. Okay? And we know from linear regression, from the linear regression of the least squares, that the SR, this should be total error squared, which is equal to ST. Right, so now the residual error from our linear regression is equal to the sum of yi minus A0 minus A1 xi squared. And if we take the difference between ST and SR, that is ST and SR, we can get an idea of how much we've improved upon our error reduction by describing the data in terms of a straight line rather than just an average value. And if we then scaled that, because we want to normalize it on the mean of different data sets, so we can actually compare different data sets, we normalize it by our true error. We end up with the R squared value, which is called the coefficient of determination, or the correlation coefficient, which is the square root of R squared. So R, the correlation coefficient, is obviously just equal to the square root of R squared. Now for a perfect fit, the sum of residuals is 0, and therefore R, or equals R squared, which is equal to 1. And this signifies that the line explains 100% of the variability of the data. And for an instance when R equals R squared, which is 0, that is sum of the residuals equals total error, then the fit represents no improvement. And that could be important for our data analysis.